Okay, so our question tonight is whether or not light gravitates. If you think of light as made of particles, as Newton did, for example, you might ask whether it's going to be deflected by the gravitational field, such as that of the sun. And actually, Newton speculated about this in his optics book, but the first calculation that is correct, at least in the Newtonian context, only appeared about 100 years later. So this was the beginning of the 19th century, but then the idea was completely forgotten, basically because throughout the 19th century, the dominant idea was that light was made of waves and not of particles. And if you think of light as being made of waves, then the question is not so obvious. Now, Einstein came back to this problem in 1911, so by which time you already had the Einstein equivalence principle, not GR. And with the Einstein equivalence principle, the result you get for a light ray grazing the sun, so passing exactly at the distance of one solar radius from its center, is 0.87 arc seconds, which is exactly the Newtonian value. On the other hand, if you do the calculation in general relativity, you get exactly twice that amount. The intuitive picture is that in Newtonian physics, you already have some sort of time curvature, but in GR, you have space curvature as well. And GR is a particular metric theory for which the two contributions are exactly the same. For other metric theories, the relative weight of the two is different. Then the obvious follow-up question is, how do we measure it? It was obvious already for Einstein that the way to do it is during total solar eclipses. So you compare the apparent position of stars when the sun is nearby on the sky with the positions of the same stars when the sun is not there. Observational searches started with a conversation between Leo Pollack, who had heard of the idea from Einstein in Prague. Pollack was visiting Berlin Observatory, and he had a chat with Erwin Freundlich. And Freundlich contacted his friends and his friends' friends and so on. And between 1911 and 1918, several attempts were made to detect this effect, some of them using archival data that existed previously already, others using data obtained for this purpose, so going to total solar eclipses and so on. But all these attempts failed for several reasons, and if you're interested, I can give you a lot more detail later on. The first expedition that succeeded is the now famous May 29, 1919 expedition organized by British astronomers. Essentially, it was conceived by Frank Dyson and Arthur Eddington. And you can think of it as one expedition or two expeditions. They were certainly coordinated, but there are things in common, but also differences. So Dyson didn't travel, but he sent his assistants, Davidson and Cromlin, to Sobral in Brazil. Eddington went to Principe Island with a clockmaker, essentially, because all his assistants had been killed fighting in the First World War. And if you want to read more about the experiment and its context and so on, a very good book is one by Daniel Kennefic, written just a few years ago in the centenary of the experiment. I should say that nowadays, when people discuss this experiment, people tend to describe it as Newton versus Einstein. That was not the main motivation, at least for Dyson. What they really wanted to prove convincingly was that light gravitated, because a third scenario would be to measure no deflection, which would show that light doesn't gravitate. So the real purpose of the experiment was to have a definitive proof that light gravitated. If additionally you could distinguish Newton from Einstein, so much the better. Okay, so here's some pictures of the expedition. So on this side, you have pictures from Sobral in Brazil. This is the two telescopes they use, a 13-inch and a 4-inch. That's one of the photographic plates. I showed you this plate already in class last week. The one in the bottom right is probably the most beautiful photo of the sun ever taken during a total solar eclipse. It's one of the photos that Eddington took in Principe Island. As I said, you can think of this as one expedition or two. The data analysis methods they did were similar but not identical. There's slight subtleties in the way they took comparison data, because you have to compare fields of stars where the sun is there with the same fields when the sun is not there. And at the time, this would mean wait for some months to get these comparison plates. They did it in slightly different ways. But in the end, they got results that are consistent with the Einstein prediction and which robustly exclude the Newtonian prediction. They wrote a paper which you can find online today. It's open access. You can read about the data analysis they did. And one of the reasons why one can say they're different expeditions is that the data analysis methods are slightly different, as you can see in the paper, and they are reported separately. So there's a chapter in the paper for each data analysis, and you can see how each one is done. There have been more recent reanalysis of the same data using more modern methods, which basically confirm the result. There's been in the history of astronomy area some controversy over a hypothetical Eddington bias, that Eddington selected the data to be used or not to be used in the analysis, trying to favor the relativity prediction. This is total nonsense. It's basically written by historians who don't understand the scientific method. If you look at the data analysis and what they did, it's perfectly correct. They didn't have the Bayesian statistics we have today, but with the statistical methods they had at the time, the analysis they did is correct. 3 years later, there was a different expedition by different groups in Australia who got the same result. So remember, 1.75 is what you expect in relativity. And from this point, the distinction between Newton versus Einstein was more or less considered settled. This doesn't mean that people didn't try continuing the experiments, as we'll see in a minute, but it was clear on which side nature is pointing. Now, let's take a small detour and talk about photographing the sun during total solar eclipses. This is the first scientifically useful photo of a solar eclipse. It comes from 1851, so it's quite old. There's earlier photos of total solar eclipses, but with very low resolution and so on. So they're not really scientifically useful in the sense that they can tell you something about the corona or something like that. Now, the Iberian Peninsula also has an historic role in these developments. So in this map, you see some eclipses of the sun whose path of totality or annularity went through the Iberian Peninsula in the late 19th and early 20th century. So you see there's one in 1860, there's one in 1900, one in 1905, one in 1912 with a very thin path. So keep that in mind. We'll come to it in a couple of minutes. There's also another one that went through the south of Portugal and Spain in December 1870. And it's sort of curious that this is the one for which astronomers in Portugal and Spain prepared the most at the time, but they were completely rained out. So it was in December 1870. It was raining all day, so no one observed it, at least in the Iberian Peninsula. So sometimes nature is unkind to you. 1860 is important. So that one, the path of totality went through Spain. It's important historically because it was the first total solar eclipse to be extensively photographed by several teams from different countries and so on. The most famous photos that were taken by this guy, Warren de la Rue, so a British astronomer, and he got the Royal Navy to give him a ship to transport lots of equipment from the UK to the north coast of Spain, and then from there to Miranda de Ebro. And that's where he took this and many other pictures. But various other people, I can mention Foucault and Angelo Secchi. Foucault, you know from Pendulum and several other things. So by this time, photographing eclipses was a widespread technique. 1900 is also interesting. So this is a map of the path of totality going through Portugal, drawn by Frederico Ohm, who was an astronomer in Lisbon. For this eclipse, the Greenwich Observatory sent an expedition to Portugal, which set up a base camp in Ovar. And this was led by William Christie, who was the royal astronomer at the time. And Christie's assistants also came along. One assistant was Frank Dyson, who became astronomer royal by 1919, so he actually succeeded Christie, and Charles Davidson, who was one of the people who went to Sobral in Brazil. So this tells you two things. First, major observatories were used to sending expeditions to most solar eclipses, at least the ones where the access was relatively easy and where they thought that the observing conditions would be good. And second, in most cases, it was the same people going in these expeditions. So people, you don't have total solar eclipses every day, but throughout 10 years, 20 years, you accumulate experience. So these are experienced people. They're not novices that are trying to do things for the first time. This eclipse is also famous because it's the first one to be filmed, or at least the first one for which a film survives. So this was done in the US, not in the Iberian Peninsula. It's actually a remarkably good movie, considering it was done in 1900 and that light conditions changed significantly during totality. So if you ever seen a total solar eclipse, you can more or less relate to what you're seeing. Although I should say that, in my opinion, a total solar eclipse is the only natural phenomenon that you cannot grasp by looking at a picture or even a movie. An aurora, a comet, an annular eclipse, a total lunar eclipse, you can more or less get from pictures. Total solar eclipse is just completely different. You have no idea unless you're there experiencing it. Okay, then I mentioned 1912, and this is actually an extremely interesting one. This was, let's call it a hybrid eclipse, or at least a potentially hybrid one. So, depending on the distance of the moon, you can have a total or an annular eclipse. If the moon is nearby, the whole sun is covered and you get a total one. If the moon is a bit far away, it cannot cover completely the sun and you get an annular one. Now, if the moon is at the right distance, you can have a hybrid eclipse, meaning that at the ends of the path of totality, you get an annular eclipse, but somewhere in the middle, the moon is right at perfect distance, and you get a total eclipse just for a bit. Now, at this time, calculations were not precise enough for people to know whether the eclipse would be annular or hybrid, meaning total in a small patch of the of its path of totality. There were different calculations by different observatories that led to different results. In the end, the result was it was a hybrid eclipse. It was total in a narrow area, just going over Portugal, that narrow area you saw. But totality only lasted 2 seconds. So it's almost the shortest total eclipse you can ever get. Now, if you're an amateur and just want to see a beautiful sight on the sky, 2 seconds is really lousy, right? You don't travel across the world for 2 seconds, unless you're really crazy for eclipses. But if you're an astronomer, this is what you want, because knowing whether or not it's total and in which place it's total, tells you a lot about the orbit of the moon, the sizes of the sun and the moon, the shape of the moon. It's not a perfect sphere, there's craters and so on. So this is an extremely interesting eclipse from the scientific point of view. So there are several expeditions, some to Portugal, some to Spain, because people were trying to guess where it would be total, if it was total. This eclipse also was filmed extensively. So we're talking 12 years after the movie I've just shown you. It's known to have been filmed at least in Portugal, Spain, France, Belgium, and Germany. And another curiosity relating to Portugal is that the person you see in the photo, an astronomer called Francisco Costa Lobo, was an astronomer in Coimbra, and he was one of the pioneers of astrophysics in Portugal. He's known to have filmed the eclipse with the help of a military guy called Tenente Ferrão, who was an amateur photographer and cinematographer. And this is known and reported by many people to be the first scientific movie ever made in Portugal. Unfortunately, as far as I know, it's lost. I've been trying over the last six months to find it. I've contacted lots of colleagues in Coimbra. I've contacted Cinemateca Portuguesa. Lots of people know about the movie. They know it has been made, but no one has a copy of it. So I'm still thinking of possible routes to try to find it, but maybe it's just completely lost. Now, since in Portugal there had been the previous eclipse in 1900, for this one there was a sort of public information campaign. So here you see 2 pages of a magazine called Ilustração Portuguesa, which is a weekly magazine published by a newspaper called O Século, where an astronomer from Lisbon called Mélio Simas wrote a short description of what the eclipse would be and what people would see and so on. So this is written at the end of March. And another interesting aspect is that if you read over there, at least those of you that can read Portuguese, this is, as far as I know, the first citizen science experiment in Portugal. So people were asked to report from where they were, whether they saw a total eclipse or not, whether the sun was completely covered by the moon. In case it wasn't, where the sun was not covered, is it in the north part, in the south, and so on, and to report exactly where they were, where they made the observations. Because if you have lots of these observations, by triangulation, you can figure out exactly the geometry of the eclipse and the positions of the sun and moon. So this is an interesting experiment that Mel Simas clearly understood could be done. So here's some photos of the time. Up here you see Lisbon Observatory. They didn't bother to send an expedition to Ovar. So they just stayed in Lisbon and, of course, observed a partial eclipse. At the top, you see two photos taken in Lisbon during the eclipse. And this is the group that was in Ovar. So there's the Portuguese expedition and several others. So here you have, on the left, the leader of the French expedition. On the right, two people from the Russian expedition. And here's the Portuguese group. So the second person from the right is Costa Lobo. Next to him are some of his students. And towards this side, so this is the camera that they used to make the movie. So people know what camera it was and all of that. Everything survives except the movie, which is annoying. Now, I said, despite the fact that by 1922 the result was sort of settled, people kept trying to do the experiment, and with mixed success. So over the years, some people more or less succeeded, some people failed for various reasons. It's still a very challenging experiment. The last of the classical era of these experiments was done in 1973, so 2 years after I was born. So it is an expedition from the US to Mauritania, who got a result which is again consistent with Einstein, but with a significant error bar. In the 1970s, things changed because radio telescopes were then available, and it became possible to do the same kind of test with quasars that are occulted by the sun. So the sun is not very bright in the radio, so you can observe sources in the radio band being occulted by the sun, so bright quasars, for example, and do the same test without needing to move radio telescopes or go to wild places. So this is an example of a new technique to do the same kind of measurement. Others emerged later. Nowadays, you can do this from space. So the Hipparcos satellite did it a few years ago. Gaia is doing it now. They'll publish new results next year and so on. Nevertheless, with the centenary of the experiment, people became interested again. And in 1917, Don Bruns in the US, using essentially sophisticated amateur equipment, repeated the experiment and got this number, which is so far the most precise and accurate result using the original method. US colleagues tried to do the same last year. In principle, last year's eclipse was a bit more favorable than 2017, but for various reasons, they got a result that is, although consistent with general relativity, a bit worse in terms of precision. Now, I've been talking about this number, 1.75 arc seconds, which is sometimes called the Einstein constant or the Einstein coefficient. But the more modern way of phrasing these constraints, which you see in that diagram, for example, is a parameter gamma, which is called the Eddington parameter, or more technically, more accurately, one of the Eddington parameters. Now, this gamma is essentially the ratio of space curvature to time curvature. So for general relativity, gamma is 1. For Newtonian physics, gamma is 0, because there's no space curvature. So it's just technically easier to use this gamma because you can relate it to other observations that you can do in cosmology, for example. So this is a picture of the 2017 eclipse in the US. It's several stacked images with different exposure times. That's why you see more or less of the corona. You can actually see, although the moon is in the new phase, you can actually see so the phase facing us from light bent by the Earth's atmosphere, which is kind of cool. It just tells you how sensitive these detectors are. And in this plot, you have various measurements. So the ones from 1919, the ones from Don Brunt, and several others. So this is the deflection that you get as a function of distance from the sun. So you get 1.75 arc seconds at the distance of one solar radius. As you move away, the deflection goes as 1 over the radius, so it decreases. And you see, you get what is consistent with Einstein's prediction, but there's still a significant scatter, which again shows you it's a technically challenging experiment. Now, why am I telling you about this? As you probably know, there's total solar eclipses coming our way. So there's one in August 12th next year, visible in Spain and just a tiny bit of Portugal. Then another one on the 2nd of August 2027, and then there's also an annular one in 2028. And just like 1919 was actually the best possible eclipse in the 20th century for this experiment, the best possible eclipse on the 21st century for doing this experiment is this one in 2027. So we developed a plan to repeat the Eddington experiment using modern techniques in 2027, but using 2026 as a full end-to-end rehearsal. So testing the equipment, testing the data reduction and analysis pipelines, and testing the people that will do the experiment. And by the way, for those of you who've never seen an eclipse, if you're not planning to travel and go outside Portugal, at least for the Portuguese ones, you really should see it next year. Because if you want to stay in Portugal, the next total solar eclipse that you can see in Portuguese territory is in 2144. I already have other plans for this year and possibly you too. Okay, why is 2027 such a significant eclipse? Well, two things. It's very long. It's the second longest eclipse in the 21st century, total solar eclipse. And the longer totality, the more time you have to acquire data. And the field of stars is very populated near the sun. The more bright stars you have, the more deflections you can measure, and that improves your statistics, everything else being the same. That agglomeration of stars that you see in the top right is M44, so the Beehive cluster, which will be in the field of view. So that's a nice place to get data. So here's what's called a Gantt chart, a simple version. It's our planning of the experiment. So we need to get the equipment, we need to test our data analysis, we need to get our own data and test it, and reduce it with this pipeline. You can also do tests during the full moon for reasons that I can explain you later. And then, as I said, 2026 is a rehearsal for 2027. Now, the idea of doing the experiment that was actually suggested by former AstroCamp students. So we put together a science team of former students that are already in university, some doing PhDs, some masters, some undergraduate degrees. So this is what they looked like when they were in the AstroCamp. These are more modern versions of them. Some of the affiliations, at least two people will change affiliation in September, October, but this is where they are now. And we've been training ourselves to analyze the data. We analyzed already the 2017 data, and we understand the pipeline and how it works. And we have some ideas for improving it. And just to give you an idea, so this is one of the fields of view of the 2017 data. So this is the eclipse sun. So notice there's two stars quite near the sun at sort of 5 o'clock and 11 o'clock positions. And it might not be obvious, but in each case, there's a blue disk, which is where the Gaia satellite thinks the star should be. And there's a yellow cross, which shows you where it was seen in the eclipse. And if I zoom in on the 11 o'clock star, so again, blue is where it should be, yellow is where we see it. Remember, the sun is at the bottom right. What you're seeing is the effect of relativity. You're seeing the curvature of space in that difference, right? The first time we got this, I got really excited about it. You're seeing general relativity with your eyes. This is a synthetic image, but you can see it in a FITS file, in an astronomical image. Just before the camp started, I was here 3 days with last year's students who remained in the program, and we started exploring the pipeline and tweaking it and seeing what measurement we get for the Einstein constant if we change several steps, several assumptions in the pipeline. So it's what's called a sensitivity study. So understanding how the result we get is affected by the assumptions we made in the data reduction and analysis. And this is what we achieved in 3 days, which is already quite good. Because to do this, in addition to understanding the pipeline, you need Python, you need to program in Python, you need to know statistics and so forth. But we're now continuing this, and we have some ideas to improve the pipeline. So to finish, so what's the plan? We are one team that will do this experiment. Our US colleagues will come as well. There's other teams. There's one from Denmark. There may be one from France. There may be one from India. And we are, again, doing separate expeditions, but in a coordinated way. So one of the things we agreed on is that we'll all buy or try to buy the same equipment. So in the end, we'll do separate analysis. Each team will do its own analysis. But in the end, having the same equipment, we can combine the data and minimize possible systematics and so forth. Students from next year's AstroCamp will participate in the expedition. We'll go to Spain. We'll not stay in Portugal. The same should be the case in principle for the 2027 eclipse. And students from previous editions who are still in the program can join us as well if they can be included in a smooth way in the team. Because remember, there's already 15 or more people that have been working in the project for a year. So people need to be ready to join it smoothly and take up some tasks in the project. We have some ideas for additional activities to be done in schools. This is not ideal because the eclipse is in August and schools are closed, but we have some ideas that we'll try to sell to schools. With a colleague, I already have a certified teacher training course. So we'll give it from October to December. So teaching school teachers not only about astronomy in general, but specifically giving them some tools to prepare for these eclipses. There's also some ideas for a possible national program for these 3 years, which are being discussed with CNC Viva. I don't know if they'll go very far, but we can try. And finally, in the long term, our idea and this is actually the initial motivation for the US colleagues, but I think it's an excellent idea, is to take this from a cutting edge experiment to a standard experiment. What do I mean by that? So for the moment, only one living person, which is Don Bruns, managed to do this successfully with a good level of precision and accuracy. So this is more challenging than being an astronaut or even going to the moon. Only one living person managed to do this. So it's still very technically challenging. Having digital equipment helps you in some ways, but it also gives you some difficulties, which I can explain at the end. But ideally, what we'd like to do is to make this a canonical experiment. So when you are an undergraduate student studying physics or astronomy, in your experimental classes, you do classical physics experiments, you do quantum physics experiments. Maybe you do 2 or 3 experiments that test special relativity. You never do an experiment that tests general relativity. So if you ask, what is the closest that an undergraduate student could come to doing a general relativity test, I think the answer is this one. Obviously, you don't have total solar eclipses every day or every year, or you don't have them in nice places, but there are two ways to go around it. One is we can make all the data public, and we committed to eventually putting all the data that we gather publicly available. Also, the data reduction and analysis codes will be public, and everyone in a university or even a high school can download the code, can download part of the data. And as long as people can program in Python and know a bit about observational astrophysics, they can do their own test and analyze their own data. But there is also a second alternative, which is to do the test during the full moon. Because the brightness of the sky near the moon during the full moon is very similar to the brightness of the sky near the sun and the moon during a total solar eclipse. Now, the gravitational field of the moon is, of course, very much smaller. And with equipment like this, you're not going to get a detection of a deflection from the moon, but you should get a null result. You should get a result consistent with 0. In other words, if you did your experiment correctly, you should get 0 plus or minus something arc seconds. If you get a supposed detection, then something is wrong in your experiment. And this is, pedagogically, this would be an excellent experiment, right? Because if you're wrong, you will know you're wrong. And then there's no doubt that your analysis or your data acquisition will be wrong. So I think this would be an ideal experiment for a university course. And here you have a full moon each month. So okay, you might be rained out or something like that, but in principle, it's something that you could do over a semester or one academic year. So that's the long-term plan. So hopefully if you succeed 10 years from now, people going to university and studying physics will have to do this test at some point. Okay, and that's what I had to say. So we'll see how this develops in the coming years. So there's lots of work to be done still, but I think we're on our way, and we'll see what we get. And that's it.